Okay, so yesterday we talked about the two different kinds of latent heat, and we said that one of the kinds of latent heat, okay, is the latent heat of fusion, and that has to do with when either ice or solid water turns into liquid water or vice versa. Okay, liquid water freezes into ice or solid water. Energy is either needed or given off in that process. So in order to melt ice, obviously energy is needed. So heat goes in, okay, for that process. And when water freezes into ice, energy is given off, okay, which is oftentimes why you can actually see steam coming off of a lake when it gets really, really cold out. Right? You're seeing essentially the energy being given off as that liquid is changing into ice. Okay, it has to release energy in order for that to happen. The other type was specific latent heat of vaporization, which is the energy that is either required in order to evaporate water into its vaporous state, or the energy that is given off when water vapor condenses back down into liquid. Okay, and we said that this latent heat is one of the ones that is very, very important, okay, in terms of energy transfers from equatorial areas to more northerly areas on Earth. Okay. Via the wind. All right, so bringing in warm, moist bodies of air that contain lots of water vapor. When that water vapor condenses, we get the heat, okay, that was used to evaporate it being delivered to us. All right, so they represent, latent heat of vaporization represents a major energy transfer mechanism, okay, for the planet as a whole. Now, we were looking at this heating curve of water here yesterday, and just a quick review of what was going on in here. Okay, we've got heat being added on the x-axis, and we've got the temperature of the material, in this case water, okay, on the y-axis. So if we start at minus 25 degrees, obviously water is in a solid state. As I add heat slowly to that, okay, the temperature of the ice increases until it gets to what? 0. Ice cannot exist above 0 degrees Celsius. Okay, so the ice begins to change state. While the ice is melting, changing state into a liquid, the temperature does not change. All right, it is really important to understand that in terms of thermal energy, you can only change kinetic thermal energy or potential thermal energy, but not both at the same time. All right, so when you're changing the state of a material, okay, the temperature is going to remain the same until the state change is complete, at which time then the kinetic thermal energy will begin increasing. All right, so once I have liquid water, if I continue to add heat, the liquid water will heat up until it gets to 100 degrees Celsius. The liquid water will stay at 100 degrees Celsius until all of it has boiled off and become a vapor, at which point the vapor will begin to warm up and go up to whatever temperature you heat it to. All right, everybody with me there? All right, so on this part of the graph here, we are dealing with, okay, the latent heat of fusion. Okay, and on this part of the graph, we're dealing with the latent heat of vaporization. The other parts of the graph, we're dealing with kinetic thermal energy. And we've already used a formula that helps us to calculate how much kinetic thermal energy is required to warm something up. Anyone remember what it is? You just used it on yesterday's quiz. What's that? E equals mc delta T. Okay? You use that formula to calculate the amount of energy being put in anytime the temperature is changing. So on this heating curve of water, when we start doing calculations to do with this, okay, E equals mc delta T is going to get used anywhere where the line is diagonal. All right, so we'll use it there. E equals mc delta T. We'll use it here. All right, and we'll use it here. Oh, sorry, not there. Sorry, on the other diagonal part, not the horizontal part. All right, is that an easy formula to use? And you don't have to manipulate it, because it's already set up to find energy, okay, when we're using it in terms of the heating curve of water. So all you're going to have to do is plug numbers in. The one thing you will have to remember, though, is what C, what specific heat capacity do you use? What are we dealing with here? Water. However, look on your chart of specific heat capacities. Water's weird. It's a polar molecule, which means it has strange behaviors. That is, the specific heat capacity of ice, liquid water, and steam are all different. Okay? The specific heat capacity of ice is 2.116 joules per gram degree Celsius, while liquid water is 4.2 joules per gram degree Celsius, and steam is 2.02 joules per gram degree Celsius. They all have a different specific heat capacity, right? I mean, it's not that hard to remember that you have to use a different one. You don't have to memorize them, okay? Because they're going to be on your test or your formula sheet anyway. All right, let's look at, okay, specific latent heat of fusion specifically here. All right, so when we're melting or freezing, that's what we're dealing with, the latent heat of fusion, which is often abbreviated as L subscript F. Okay, so we usually just say LF. This is the amount of heat required to melt 1 gram of a substance with no change in temperature. All right, remember that when a state change is occurring, temperature is not changing. Okay, so there's no temperature change during the melting process as potential energy is increasing, not the kinetic energy. The latent heat of fusion for water is 333 joules per gram. Okay, 1 gram of liquid water is 1 milliliter. How much is a milliliter? Is it very much? It is not. Okay, a can of pop has 355 milliliters in it, so you can imagine that a milliliter is not very much water. All right, 1 gram of ice would be about the size of maybe a peanut. All right, we're not talking about very much ice, but it takes 333 joules of energy to melt that much ice. That's already at 0 degrees. All right, it would take even more if it was colder than 0 and you actually had to heat it to 0, okay, and then make it melt. So it takes a lot of energy to melt ice. That's why ice is so effective at keeping drinks cold. All right, when you put in a couple of ice cubes, okay, you're probably putting in, let's say, 50 grams worth of ice. All right, so there's a lot of ability to absorb heat from your drink and from the surroundings. So it has the potential at least to keep your drink cold for a significant amount of time. All right. Jack, you want to put that phone away? Thank you. Is that making sense? All right. So at 0 degrees Celsius, 333 joules to melt 1 gram of ice. Okay. On the other hand, when 1 gram of water freezes into ice, that much energy is released, okay, is given off. All right, so the formula that we use here to figure out how much energy is required, E equals mass times LF. So however many grams you have multiplied by 333 will give you how much energy would be needed to either melt ice or how much energy would be given off when that amount of water freezes into ice. All right, everybody with me there? Now, if I have 20 grams of ice and I melt it, how many grams of water will I get? 20. Okay? The volume won't be the same, but the mass is the same. All right? I can't create or destroy matter, if you recall from Unit 1, the law of conservation of mass. Okay, says that matter can't be created, can't be destroyed, right? All right? So when I convert something from a solid form to a liquid form, I have to have the same amount of it. All right? We know that obviously ice takes up more space than liquid water, but it has the same mass as liquid water. All right, so first example here. Okay, how much heat would be required to melt 3 grams of ice cubes placed in a food cooler? All right, well, we know our formula is E equals MLF. All right, they told us that we're dealing with 3 grams here. All right, so 3 grams times the latent heat of fusion of water, 333 joules per gram. All right, what does that give us? 999 joules. Okay, making sense? All right. Now you know why your hands get so cold when you make a snowball with your bare hands. Okay, when you make a snowball with your bare hands, you're probably dealing with between 100 and 250 grams of snow, all right, or grams of ice. And that's a lot, all right? There's no way. I mean, you would get frostbite if you held that much snow in your hands, and we all know how hard it is to hold that snow, that much of it in your hand for very long. Okay, you would get frostbite most likely on your fingers, all right? As you melted that ice, it would take all of that energy away. You would start to feel cold, right? That's why you feel really cold if somebody, grabs your jacket and shoves a bunch of snow down your back. Okay, right? It's chilling because, well, it takes the energy from your body to melt all of that snow, and we're talking for every gram, 333 joules of your valuable body heat. Okay, and so it very quickly can make you very, very cold. All right, everyone follow me on that? Okay. Hey, specific latent heat of vaporization. So when we're boiling, okay, or we are condensing here, okay, latent heat of vaporization is 2,260 joules per gram. Right? That's why when you look at this graph, you can see that the amount of energy required to melt the ice is a lot less than the energy required to evaporate the water. Okay? To vaporize water, to turn it into a gaseous state, requires way more energy per gram, okay, than to melt ice. 2,260 joules for every milliliter of water. All right, that's huge. All right. So when you sweat, okay, do you have the potential to lose a lot of energy by evaporating your sweat? Yeah. Right? Especially if you sweat heavily. Although, even if you don't sweat heavily, a lot of your sweat just drips off of you, okay, and doesn't end up using energy from your body to evaporate. Okay, but for most of us, if we only perspire lightly, most of that will evaporate, okay, and it will help to cool us off. If you're working really, really hard and you're sweating buckets, well, okay, you're probably not getting as much benefit out of all of that sweat as you probably could. All right, and everyone knows some people sweat more than others. Okay, guy who used to be the Edmonton Oilers goalie, Nikolai Habibulin. Okay, he sweats. He sweats so much that he can lose like 10 pounds in a game. Okay, that's the equivalent of between 3 and 4 liters of water. Okay, this guy has holes drilled in the bottom of his skates so that the sweat can drain out of his skates. They actually caught it on the goalie on the goal cam once, okay, because it's down by ice level, and you could see the water dripping, the sweat dripping out of the bottom of his skates one time. Okay, this is a guy who every 10 minutes, whenever there's a break in the period, he goes to the bench and gets a new glove, okay, and blocker, because they can go like this and sweat flies off. All right. Now, okay, is he getting the benefit out of every milliliter of sweat he's perspiring? Absolutely not. There's no way. Okay, you'd freeze to death evaporating that much sweat. All right, but okay, some people perspire more than others. All right. Now, on a really hot day, how many people like to go get a Slurpee? I don't care if it's hot. I go get a Slurpee even when it's minus 30. I love Slurpees. Okay, but it cools you off, doesn't it? Okay, why? Not just because it's cold, it's also it's frozen. Okay, when you drink that down, you're drinking ice. Okay, and for every gram of it you put in your body, 333 joules of your precious body heat is used to melt it and then raise the temperature of the now liquid Slurpee, okay, up to your body temperature. That's why it's so refreshing. Okay, you drink a Slurpee and yeah, okay, you can feel a lot better, a lot cooler, sometimes even chilled, right? If you do it too quickly. If you drink it too quickly, how else might you feel? Brain freeze. Okay, what causes brain freeze? When you swallow. This really cold substance runs down your esophagus, which is right next to your carotid arteries. Your carotid arteries carry blood to your brain. Your brain doesn't like getting cold blood. It hurts. Okay? So, rapidly you get this sensation of acute pain in your head, okay, because the blood going essentially to the muscles surrounding your brain, okay, or the muscles on your scalp, okay, is very, very cold, and they contract quickly, okay, and they give you this sensation of a slurpy headache or brain freeze, okay. That's what causes it. You will rapidly cool the blood in the carotid artery, okay, and that can give you that sensation of brain freeze, okay, as a result. All right, so the formula for this one, very similar. E equals mass now times LV. Okay, so instead of the latent heat of fusion, now we use the latent heat of vaporization. All right, so if we're looking at this example here, how much heat is required to vaporize 2.5 kilograms of water that is already at 100 degrees Celsius? All right, well, if I want to figure that out, E equals how many grams in 2.5 kilograms? 2,500. Okay, times 2,260 joules per gram. $5,650,000 joules. All right, now that's 2.5 liters of water. Right, 2.5 kilograms is 2.5 liters of water. Okay, I mean, you would never evaporate that much water off of your body, obviously. Okay, but does that much water evaporate off of lakes and ponds and sloughs and stuff? Yeah, way more than that actually evaporates in a day. Right, if you look at maybe like a small puddle on your street after a rainstorm, okay, that puddle is gone in a matter of hours. Right? Because there's a lot of energy available there. The road is usually warm. It warms up quickly when the sun shines on it. Okay, and all of those things can contribute to how quickly it would evaporate. Okay, it's making sense so far? All right, here's where we're headed. Okay, let's do this. We'll take our heating curve of water picture here, and we'll just copy it over. Okay, I want you guys to write this down as an example. How much energy would be required to heat 55 grams of ice into steam? Hey, sorry. We got to give the initial temperature here of ice, let's say at minus 15 degrees Celsius, into steam at 120 degrees Celsius. All right, write that one down. And I'm going to give you a couple minutes and see if you can figure out how to do it. Okay. We got to do a couple of things when we're heating ice into steam. Okay? First thing is that we're starting at minus 15. If I start adding heat, what's going to happen to the ice? Okay, everyone says it's going to melt, but it doesn't melt right away. First it heats up to 0. Then it melts. All right? So our first step here, if I want to heat ice into steam, my first step is that I have to heat the ice until it gets to 0. All right? How do I figure out how much energy would be required to change the temperature of ice? E equals mc delta T. Anywhere where the temperature is changing, like right here, okay, I use E equals mc delta T. So in step 1, okay, so we're going to label that as step 1, E equals mc delta T. All right? I was told M is 55 grams. Okay, I'm dealing with ice. So the specific heat capacity of ice is 2.116 joules per gram degree Celsius. And how much am I heating the ice by? 15 degrees. Most common mistake I see on a question like this is someone says they heat the ice by 135 degrees. Because it goes from minus 15 to 120. I'm pretty sure it's not ice at that temperature. Agreed? Okay, you can only use the specific heat capacity of ice while it's actually ice, and that's only to 0. Right? So the temperature change is from minus 15 to 0. All right, so that's our first step. Okay, 55 times 2.116 times 15 degrees. All right, so we're looking at 1,745.7 joules. All right, so that's how much energy is needed just to get the ice to 0, where it will now start to what? It'll start to melt. All right, what formula should I use right here in step 2 when I am melting the ice? What formula do I use to figure out how much energy that's going to take? M times LF. Okay, the mass of the ice times the amount of energy required to melt every gram of it, which is 333, the latent heat of fusion of water. All right, so step 2, okay, E equals MLF. Right, so down here in step 2, we always use LF. Okay, in fact, we always use E equals MLF. All right, mass is still 55 grams times 333 joules per gram. All right, so we're looking at 18,315 joules. Okay, is that a lot of energy? A lot. Compared to how much it took to heat it up, it's more than 10 times as much. Okay? Changing the state of something requires way more energy than changing the kinetic energy of it. Okay? All right, so now we're done step 2. Now I'm here. I now have liquid water at 0 degrees Celsius. If I continue to heat that water, what's it going to do? It's going to heat up. It's going to change temperature. What formula do I use to figure out how much energy is required to change the temperature of something? E equals mc delta T. Okay? I'm going to use that formula in 3 different places. Anywhere where the temperature changes. Here. Okay? And here. All right? So, now I'm going to figure out for step 3, okay, how much energy is required to heat the water from 0 to 100. Right, it's only water between 0 and 100. All right, so mc delta T. All right, 55 grams. I haven't changed the amount of water I have. Okay, times now the specific heat capacity of water, 4.2, times the change in temperature, 100 degrees Celsius. Yeah. All right, so we've got now 23,100 joules. All right, so now that I've done that, now I'm here. I now have boiling water at 100 degrees Celsius. I continue to add heat. The water continues to boil. Does it change temperature? No. It can't change temperature while it's boiling because it's changing state. Okay? We can't change temperature and change state at the same time. Only one or the other can happen. All right, so in step 4, I'm changing the state of liquid water from liquid to gas. What formula do I use there to calculate the energy? MLV, right? Okay, because now I'm vaporizing the water. So I use the latent heat of vaporization. All right, so for step 4 then, here's what we got. E equals MLV. 55 times 2,260 joules per gram. All right. All right, so we got 124,300. right? And that's joules. Okay, so that's step 4. Okay, has any of this math been difficult? We're not even manipulating here, right? We're just plugging in numbers. All we have to do is remember what formula do I use at what step on the curve. All right, all those formulas will be given to you on your exam. Okay, all of the heat capacities and latent heats. The two of you can get out. Both of you, go. Yeah. Okay, both of those. Okay, all of that stuff will be given to you on the test. You don't have to memorize it. The only thing you got to remember is that ice melts at 0 and water boils at 100. I think you probably all knew that before. Okay? You guys with me there? All right. Step 5. Go back to the heating curve. Now I have steam at 100 degrees Celsius. If I keep adding energy, the steam will increase in temperature, which means if I want to calculate the energy, I have to use the formula that has temperature change in it. E equals mc delta T. All right, 55 grams times the specific heat capacity of now steam. Okay, and then by the temperature change. And we said we were going to heat it to what, 120? Okay, so how much am I changing the temperature by? 20, because I'm already at 100. Hey, 2,222 joules. Okay. That's as long as one of those questions could possibly get. On an exam, I would never ask you one that goes all the way from ice to steam because it takes too long. Okay? What do I have to do with all of those numbers? Add them up. I want the total amount of energy required for that whole operation. All right? So I take my 2,222. Okay, I add my 124,300. All right, and then 23,100. Right, and 18,315. And 1745.7. All right, so 1,069,682.7 joules. Okay, you want to draw this diagram roughly, all right, for any latent heat question. So if I give you a latent heat question, okay, the first thing you want to do is go and roughly draw the latent heat curve. You don't need to draw the whole graph. You know that this is at 0 and this is at 100, okay? And then mark where you start and finish. So if the question said you want to heat water from 30 degrees into steam at 130, mark your starting point. Mark your ending point. Every place the line changes direction is a new step. Step 1, step 2, step 3. Okay, with me there? All you have to remember then is what formula do I use at each step. Okay? Making sense? Okay. I want you guys to answer. Okay, let's say 1 through 4 for right now. Okay, complete sentences. Okay, to explain those questions, and then we'll look at 5, 6, and 7, and 8. Okay, after that. So 1 through 4 for right now, please. So for number one we already talked about. Okay, you put ice cubes in your drink because not only are they around 0 degrees Celsius and as a result most likely colder than your drink. Okay, but they're solid. And that means they have the potential to absorb large amounts of thermal energy from whatever liquid they are placed in. Okay? Because it takes a lot of energy to change their state from solid to liquid. All right? So, just putting 0 degrees Celsius water in your drink, well, first off, yuck, because it's going to dilute your drink. Okay? But secondly, it's not going to do very much because it's already a liquid. It doesn't have that extra 333 joules per gram, okay, of potential energy absorbing ability that ice does. Right? So ice has this ability to absorb large amounts of energy that a similar substance that doesn't have to change state wouldn't be able to. Okay, we talked about sweat as well. Okay, sweat cools you because it takes energy from your body in order to evaporate it. 2,260 joules for every milliliter of sweat that you evaporate off your body. Okay, now in the real world it doesn't come down to exactly that much because the wind can help, okay, and the sun can help evaporate and stuff like that. But okay, for the most part, you're still losing a lot of energy to your sweat. Okay, and if you're losing energy to the sweat, then you're getting cooler as a result. Now, what about your dog or your cat? Okay, they don't sweat. How do they cool off? Right, they pant. Okay, panting works kind of like sweating, except it doesn't use as much water. All right, when they pant, water evaporates off of the back of their throat as they push air past it. Okay, and that cools the blood in the carotid artery in the same way it does when we drink a Slurpee. Okay, and so the blood going to their brain is cooler, and it helps to cool them off. All right, so essentially that's what they have. They also have, the fur and stuff like that. Fur can insulate both ways, okay, in a lot of cases. So, okay, things like that will help to cool them off. All right, but obviously sweat works really good at cooling you off. The problem with sweat is, if you're in the desert and you're using it to cool yourself, you're not going to last very long, right? Because you're going to get dehydrated very quickly. Whereas, an animal like a camel or an antelope, okay, that doesn't sweat can last a lot longer because it doesn't waste water. Okay. Number 3, gardeners often spray their crops before a frost, and this prevents the fruit from freezing. Why? Do we want it to get colder? We want it to lose temperature? Okay, so we're not spraying. We're spraying it with water. That's all they do. They turn on the irrigation and they get their crops nice and wet. Okay, now when the temperature starts to cool, the water that's on the outside of the fruit cools as well, and eventually the water on the outside of the fruit might start to change state. What happens to the energy from that water as it freezes? It goes into the plant. Okay? Remember that water releases 333 joules for every gram when it freezes into ice. So if you coat your crop with water, then as the water starts to freeze, the energy from it, some of it goes into the fruit, some of it goes into the surroundings, but usually enough of it, okay, will go into the fruit or the leaves of the plant or whatever to protect them from a light frost. If it's going to be a heavy killing frost, it isn't going to matter. All you're going to see is icicles all over your plant, okay, and your plant will still be dead. All right? We know that we have to watch out in the spring and in the fall, okay, with things like peppers and tomatoes and stuff like that because they're not frost tolerant. You have to cover them up, okay, things like that. All right? Spraying them with water could protect them as long as it doesn't get too cold for too long. All right? If it drops down to -5, they're cooked anyway. Right? But if it's only around like 0 or -1, it might protect them, okay, as long as it doesn't stay that cold for that long. Okay, and number 4, which is better at keeping food in a cooler cold, 10 kilograms of ice at 0 degrees or 10 kilograms of water at 0 degrees? Ice. Again, it has less total thermal energy than water, which means it can absorb more energy than water can, because it still has to change state. And for every gram of ice, that's an extra 333 joules of warmth that can be absorbed from your food. All right, so ice is certainly better. All right, now for 5, 6, 7, 8, okay, and all the rest of them down here, okay, these are the problem-solving ones, okay, that we were looking at just a little bit ago, okay, when I showed you the example of the 5-step problem, okay, these are, all right, the same idea, except some of them are maybe only 1 step, or some of them are only 2 steps. And as you get further down, eventually 5 steps. Okay, so what I want you to do is answer these questions. Okay, the answers are on your sheet. Okay, so you can see if you've done them right. I'll give you a few minutes, and then we'll go through maybe 5, 6, and 7 together here. All right, so get started on 5, 6, and 7. I guarantee you guys there will be a latent heat problem on your unit exam, and it will be worth between 6 and 8 marks. Okay, these are 6 to 8 fairly easy marks because you don't have to do any manipulating. All you got to do is remember that water melts or ice melts at 0 and water boils at 100. Okay, and what formula to use. You don't even have to remember the formulas. Okay, the formulas are on your sheet. You just need to know when to use them. Yep. Okay, let's look at number 5 here. All right, so on number 5, remember I told you the first thing you want to do is draw a rough version of the heating curve of water and mark your end point and starting point. Okay, how much heat is given off when 2 kilograms of water at 0, so that's right here, freezes into ice at 0. So there's the end. Okay, how many steps is that? 1. Right? All I'm doing is freezing the water into ice. And what formula do I use right here at this step? Which formula tells me how much energy is needed to melt or freeze? E equals MLF. Okay, so then all I have to do is plug in my numbers. E equals 2 kilograms, or 2,000 grams, okay, times 333 joules per gram. Okay, when we do that, we get 666,000 joules. Okay, so guys, what you might want to do, okay, is on your diagram of the heating curve of water there in your notes, is write on here which formulas do I use at each step. Okay, that's how it goes. Right, those are the formulas you use at each point on the heating curve. Okay, so quickly, number 6, pretty much the same, except instead of using MLF, we're using MLV. Okay, it's only one step. We're evaporating water into steam. Okay, so we're only dealing with this part of the heating curve. So it's just E equals 60 grams times 2,260 joules per gram, and that should give us 135,600 joules. All right, everyone with me there? All right. We got a few minutes left here. All right, keep going on 7, and we'll go through hopefully 7 before class is over today. If not, we'll go through 7 tomorrow, and then we'll finish up the others. Okay, because like I said, you're definitely going to have a latent heat problem on your unit exam.
Good afternoon, staff and students.